In this video, my goal is to demystify the density of states function, show you where it comes from, and show you how to use it. To begin with, I'll walk you through the development of a function that expresses the number of states in a conductor, the density of states. It also makes sense to divide out the volume of the conductor, L cubed, up here to get the density of states per unit volume. I'll limit this treatment to the cube of dimension L by L by L because shape really has nothing to do with this. It's a property of the material. To answer our first question, how many electrons, big N, are in this cube, I need to make a little bit of an argument. And that argument is that the number of electrons there are per energy level in the semiconductor times the number of energy levels is the number of electrons. And given the large number of energy levels, don't be surprised when everything turns into an integral. Let's hash out these two quantities in parentheses that have to do with energy by rephrasing what they mean. Consider an energy level to be some discrete range of energy, and it's going to contain a certain number of states. Let's call that number of states d of e dE, because big D is the density of states. It's the number of states per unit energy. And the number of electrons per energy level answers the question of how many are home. It's the number of electrons that occupy each one of these states. And F of E, the Fermi function, answers that question. The Fermi Dirac distribution, F of E, is the probability that a state is occupied. So let's write it this way. Big N, the number of electrons, but only between energy level E and E plus delta E, is the product of the density of states, D of E, times the increment of energy. So big D of E times delta E is the number of states contained within an energy range of delta E, times the probability that each of those states is actually occupied, F of E, the Fermi Dirac distribution. And that is the number of states in energy range E to E plus delta E. So what I need to do is evaluate this expression, N, the number of electrons in the range delta E, at an energy level E, and then jump up delta E and evaluate this expression one more time at a new energy level, E plus delta E, and then jump up delta E again and evaluate this expression one more time and continue doing that. So you can see how this turns into an integral. In the previous lecture, I described the Fermi function F of E. It's a perfect step function at zero temperature, where the step occurs at the Fermi energy. As you get to elevated temperatures, like room temperature, it begins to round out, and this somewhat exaggerated rounding is shown at perhaps room temperature. And at low energy, the Fermi function has a value of 1. At high energy, the Fermi function has no value. Right at the Fermi energy, the Fermi function passes through a value of 0.5. We'll find it unnecessary to use quite so complex a function for the Fermi Dirac distribution as we described last time, because at elevated temperature we can employ the Boltzmann approximation, and so F of E will be a simpler expression. We'll see that coming up. So go ahead and sum these up from energy of 0 to infinity over all the energy increments. Keep stepping through equally sized steps, delta E, from where E sub I is the particular energy level, and add them all together to get the total number of electrons in the semiconductor. And hopefully this looks like an integral to you. So do it instead as an integral, from energy of 0 to energy of infinity of the Fermi function times the density of states function as the integrand. And that will give us the total number of electrons contained in that cubic conductor. The integral stays finite because the Fermi function becomes very small as energy becomes very large. So you never get to a situation where integrating to infinite energy leads to an infinite integral. I'll go ahead and divide out the volume of the cube and call it little n, the number of charge carriers per unit volume. I think that's more useful because the number of electrons per unit volume is more meaningful than the number of electrons. Since different samples of a material come in different shapes and sizes, little n is a material property, and so that's more universal in meaning. Now, the density of states as a function of energy is hard to find, and the reason why is because it doesn't depend linearly on energy. But if it's done as a function of momentum, it turns out to be a much simpler expression. So a little bit of hindsight here. I'm going to go with the density of states as a function of momentum. d of E times the dE differential is going to have the same numerical value as density of states as a function of momentum times a momentum differential, provided this dP corresponds to this dE. That is, the increment of energy corresponds to that increment of momentum. And in fact, this density of states function is sometimes written as a function of other things like wavelength, in which case you could add equals d of lambda, d lambda. You could write it as a function of anything you want, as long as it's meaningful for the system. Worth pointing out here is that big D of E and big D of P will have different dimensions. Big D of E has dimensions of per energy, and big D of P has dimensions of per momentum. So they really are not the same function. They're definitely quite different functions. But numerically speaking, when multiplied by their respective differentials, they give the same value. So let's go back to our conducting cube. It's full of electrons, and electrons are waves. So it should be treated like a boundary value problem. If you put a wave in a box with boundaries, the boundary conditions have to be met. The wave has to go to zero at the edges, and so you get these standing waves. You get these resonant conditions. The lowest order vibration or resonance, think of a vibrating string, has a wavelength that's twice the length of the box, so half a wavelength fits inside the box. And the next resonance fits a full wavelength inside the box, and the next one fits 1.5 wavelengths inside the box, and I don't have a picture for the yet next one, which fits 2 full wavelengths inside the box. Little m, not to be confused with mass, is the index number that labels each resonant mode. So a resonant condition can be written. What are these wavelengths, these lambdas, as a function of the index m? The lowest order m equals 1 resonance has a lambda of 2L. The next one, where m equals 2, has a lambda of L, wavelength of L. The next one has a wavelength of 2/3 L, and the next one has a wavelength of 1/2 L. There's actually a pattern developing here. So given this listing of wavelengths that electrons are allowed to have inside the cube, you can also generate a listing of momenta through the de Broglie relation that electrons are allowed to have inside the cube, just by listing out not lambda, but h over lambda. So each one of these is Planck's constant h divided by the wavelength that's listed right above it. So they're the same increment here. So make sure you follow the transition from a listing of wavelengths to a listing of momenta, which is h over wavelength. So for each one of these, it's h over 2L, then next one is h over L, then h over 2/3 L, h over 1/2 L. There's a pattern here. I'll say what it is. You have 1 over 2 times h over L, 2 over 2 times h over L, 3 over 2 times h over L, 4 over 2 times h over L. Momentum is m over 2 h over L, where m is an integer, 1, 2, 3, 4, ... up to an extremely large number. This is the resonant condition for a particle in a conducting cube. There are 3 dimensions to this cube, x, y, and z, which is coming out of the screen. Resonance is happening in all 3 directions. And there's nothing that says those 3 directions are coupled. So what happens in the x direction is separate from the y and separate from the z. So I have to write a separate resonant condition for each direction, meaning there are 3 different indices: an index for the x direction, an index for the y direction, and an index for the z direction. Now you can see why I chose to analyze a perfect cube, because having different L's in each direction would add no useful information for us. So all 3 of these together give you a momentum vector, but each component is separate. Just like when a gas particle can move around, it can have x, y, and z motion, and they're not connected to each other. Now if I took the expression p sub x equals m sub x h over 2L, and I incremented m sub x by 1, then I would increment the x component of momentum by h over 2L, Planck's constant over twice the length. And same for y. If I incremented m sub y by 1, I would increment the momentum in the y direction by h over 2L. So I can divide momentum up into a momentum volume. I can make cubes of momentum and talk about the volume of those cubes. And when I do that, I'm actually talking about a momentum space. Instead of x, y, and z, we can have a space that's momentum in the x, y, and z direction, p sub x, p sub y, p sub z. And each state in the semiconductor occupies a certain amount of volume in that momentum space. Every increment of the integer moves us an amount h over 2L forward in momentum space. And so if I chopped momentum space up into cubes that each contain one state, the volume of that cube will be h over 2L times h over 2L for y times h over 2L for z. You might want to write this down, that the volume of one state in momentum space is h over 2L cubed. Here's a view of an octant in momentum space. So, like I said, the axes are p sub x, p sub y, and p sub z, as opposed to configuration space, which would be x, y, and z. So we can make a graph on here of states. If a particular state has a known momentum in the x, y, and z direction, I can put a dot in that space that indicates where that state is, and I could draw a vector p, momentum vector, that connects it to the origin. Now, given that x, y, and z are not really distinguishable in momentum space, a particle is moving around in all three, I expect there to be spherical symmetry in any function of momentum. And so I'm going to look at a sphere in momentum space, a sphere of radius p, the momentum. And I will look at infinitesimally thin shells of that sphere, shells of thickness dp. So I'll just look at a spherical shell of one octant, because with spherical symmetry, you just have a momentum p, and I'm not really concerned then with forward or backward momentum. So we're going to just look at one octant, and I'm going to ask myself, how many states are in this shell of thickness dp? To count up the number of states in this shell, let's first depict one state. And so I have a very small cube shown there. The goal is to find out how many states fit into that shell. First, I should define what is a state per volume. The number of states in the volume dp is that volume of that shell divided by the volume of a single state. So if the shell has a volume of 1 liter and a volume of a state is 1 millimeter, there are 1,000 states in that shell. So that ratio is what we need to figure out. Let's begin with the volume of the shell. How do you find the volume of a spherical shell? It's the area of the shell times its thickness. So area of a sphere is 4 pi radius squared. The radius is being called p, so 4 pi p squared. The thickness is dp. I'll multiply by 1/8 because I am only looking at one octant, and we'll account for that throughout this entire analysis, so I'm going to keep it. And if you're still wondering about the whole octant thing, I'm only considering magnitudes of p sub x, p sub y, and p sub z, because in the end we're going to turn this into a function of energy, and energy goes as momentum squared, and so there's no sign involved. And we already know the volume of a state. We just figured that out. I added what you might call the Pauli feature there, because you're going to fill this state up with electrons, and the electrons are fermions. You can only have one electron per state. However, one of them can be spin up and one of them can be spin down, allowing you to put 2 electrons in the cube of volume h over 2L cubed. So the actual volume of a state when occupied by electrons is half of the h over 2L the cube that we had previously figured out. What remains to be done now is not very complicated. Put these expressions in this word equation up here, the volume of the shell and the volume of a state. So I'll do that right now. D of p, the density of states, times dp is, we have the volume of a shell divided by the volume of a state. Do a little simplification, cancel stuff out, and have a nice packaged expression. I'll put dp at the outside of the expression just for good form. So d of p dp is 8 pi L cubed p squared over h cubed times dp. Now that needs to be converted into d of e dE. Oftentimes people will convert it into d of wavelength, d wavelength, d of lambda, d lambda, but we're going with energy here. There is simply no convenient way to work with momentum going forward. We use energy in semiconductor physics. This can be done with some pretty elementary mechanics using an expression for kinetic energy, and because we are talking about momentum, kinetic energy is p squared over 2m as well, so you can solve those together and get p, the momentum. That's p for momentum, not whole concentration. Momentum is the square root of 2me. I used m star as the density of state's effective mass of the electron, slightly modified from the mass of a free electron. Put that expression for momentum in up here, so where you see p squared, replace it with 2 times mass times e. A little trickier is what to do with dp. That has to be turned into dE. Do that by taking the derivative of this expression. Take dP by dE, so you have square root of m over 2e, and rearrange it slightly. Bring the dE from the left over to the right side. And now we have an expression that replaces dP. We can replace it with root m over 2 times dE over root e. So put that in for dP. And when you make those substitutions, you automatically have d of e dE. I'm going to go ahead and divide out L cubed. In other words, I'm going to bring this L cubed over to the other side. It's the denominator, so still the denominator on the left side. And with everything substituted in, that's my final expression for the density of states per unit volume in this conductor. Now I say in this conductor, I haven't quite made it a semiconductor yet. That's coming up next. There will need to be a modification made to this expression to account for the presence of band gaps. In other words, this is the density of states, d of E, for a free electron gas, which is a good description of a metal, but not of a semiconductor. So a free electron Fermi gas treats the electrons in a conductor like a gas that's contained inside of that metal. Just to give you a preview of what we will do next time, the modification starts counting states at the conduction band edge. And so E in this expression needs to be replaced with E offset by the conduction band edge, or rather E minus E conduction, E sub C. But for now, what we really have in this red box is the density of states per unit volume for a metal. So let's go ahead and apply it to a metal. Let's find the Fermi energy in copper given the number of electrons per unit volume. The effective mass in most good conductors is very close to the actual mass of an electron, so you could ignore that 1.01 and it won't change your answer much. To do this, we need to actually solve the integral that we have set up. That is, the number of electrons per unit volume is the integral of the density of states per unit volume times the probability that each state is occupied. This could be a real mess, except that we can make a nice simplification. Conduction electrons in a metal don't have to jump across a band gap in order to become conduction electrons. That is, they don't need to be thermally activated into a conduction band. They're already there. So the temperature dependence of the carrier concentration of a metal is very remote. We'll do this calculation at 0 temperature and be satisfied with our result. The Fermi function at 0 temperature is a very simple thing. It's just a step function, so it equals 1 for energies less than the Fermi energy, and it equals 0 for energies greater than the Fermi energy. So I can replace integral from 0 to infinity of f of E times that stuff with the integral from 0 to the Fermi energy of d of E over L cubed. So that's my rewrite, accounting for the fact that the f of E is a step function from 0 to E sub f. That's not a hard integral to solve. Put it in our density of states function we've derived, and integrate e to the 1/2 dE. The limit of E Fermi then is involved in the answer, and I've gone ahead and rearranged it for us already. What you get is this expression, comes straight out of solving this integral. And we have the Fermi function is this stuff. H is Planck's constant, M is the density of states, effective mass of electrons in copper, N is the number of carriers per unit volume. This is being done in SI units, meaning the energy is in joules, Planck's constant in joule seconds. Now we like our electron volts when we deal with semiconductors, and we like our centimeters, but MKS it is. You could do this in electron volts with a simple modification of replacing M with mc squared and then using the mass of electron in electron volts per c squared. Physicists, in fact, like to do that with a lot of equations, but we're not doing that in this course, and I haven't been covering how that type of a unit is used, so we will stick with MKS for this particular expression. And when you do, you get a Fermi energy of 1.12 times 10⁻18 joules, which then you can convert to electron volts and get 7 electron volts. That's a conductor, so next time we will go to a semiconductor. And the main change I mentioned already is to replace E with E minus E conduction, so that we start counting states at the conduction band edge. And we'll also have to consider the hole concentration, which I'm actually leaving as a homework problem for you. So next time we will talk about carrier concentration.